Hi, I'm Andrew Morgan. This is a talk on polynomial identity testing via evaluation of rational functions and constitutes joint work with Dieter van Melkebeek. Polynomial identity testing is the computational problem where you're given an arithmetic formula computing a polynomial p, and you have to decide whether or not p is the zero polynomial. This has a simple randomized algorithm. You just evaluate p at a random point. However, it's a major open problem to construct a deterministic algorithm for PIT. General purpose deterministic algorithm would be called white box derandomization, where it has full access to the formula. But there's also black box derandomization, where you consider only pseudorandom evaluations and plug them into the simple randomized algorithm. So both forms of derandomization are related to circuit lower bounds in Boolean complexity theory, and thus polynomial identity testing plays the role of a morally complete problem for derandomization, in the sense that derandomizing it should give us a great deal of insight into derandomization for general computation. On the other hand, it also explains why derandomizing this problem is so hard. And in particular, we make progress by looking at some very restricted classes of polynomials. So we're going to talk about black box derandomization, and in black box derandomization, the central object is the generator. So in PIT, generators without loss of generality take the following form. There are fresh seed variables, and then the substitutions are polynomials in those seed variables. And then what we want is that whenever p is a non-zero polynomial, making the substitution of the generator into p has a non-zero result as a composition of polynomials. And we want to do this for polynomials in some class C, such as polynomials computable by small formulas or small circuits or other models of computation. Black box derandomization, in terms of generators of this form, means you design a generator and you want a very small seed length. And then you test whether this composition of p with g is zero by doing now random evaluations of the seed variables. And the point is that as long as your seed is short, this is a lot less randomness. And in particular, as long as your seed is short and the degree of all the polynomials involved are reasonably small, then you can do a trivial derandomization of this reduced randomness algorithm. And if everything's good, then only polynomial many evaluations, in fact, can suffice. So we make progress on black box derandomization by a couple conceptual contributions and then some technical ones. So our first conceptual contribution is the use of rational functions in generators. Instead of just polynomial substitutions, the substitutions are rational functions of the seed. Specifically, we introduce a new generator, the rational function evaluation generator, and through studying it, we demonstrate that the use of rational functions as substitutions can improve understanding of the generators that we have, and arguably lead to more elegant constructions. We also take a systematic approach to studying generators by looking at their vanishing ideals. So the vanishing ideal of a generator is the set of polynomials such that when you plug in the generator, you get the zero polynomial. For any complexity class C, the generator works to derandomize PIT for C if and only if the vanishing ideal and C have at most the zero polynomial in common. So this is the importance of the vanishing ideal because it precisely captures the power of G as a generator. In particular, derandomization using a generator G is equivalent to lower bounds for the vanishing ideal of G. And our kind of overall goal with this is that by looking at the vanishing ideal, we can focus research on the generator itself, which we have some control over, rather than the syntactic classes, where it can be challenging, I guess, to study them, to say the least. Okay, so we take this approach and apply it to the rational function evaluation generator, and our technical contributions are based on this. So first of all, we show a connection between the rational function evaluation generator and the widely used Shpilka-Volkovich generator. Specifically, they have the exact same vanishing ideal up to rescaling of the variables, the xi's. So what this means for derandomization is that if you have a class that's closed under variable rescaling, such as just about any syntactic class that people consider, then SV works to derandomize that class if and only if RFE does. So this gives a really strong notion of equivalence between these generators, and therefore results for one carry over immediately to results for the other. So that's our first technical contribution. Our next one concerns looking more closely at the vanishing ideal itself. And specifically, we come up with a generating set for the vanishing ideal of RFE as well as SV. This generating set is small and explicit. For kind of fixed settings of parameters, it's polynomial in size in terms of the number of variables, and it is explicit in the sense that each generator is a very structured determinant, and small determinant. In fact, taking an appropriate subset of our generating set, you get a Grobner basis, if you know what that means. As implications of having found this generating set, we derive some tight bounds for certain properties of the vanishing ideal for either generator. Namely, we find their exact minimum degree, the minimum sparsity of a polynomial in the vanishing ideal, and if you know what set multilinearity means, we find the minimum partition class size for the set multilinearity structure. We also use the lower bounds derandomization equivalence in reverse. Because SV is known to derandomize some classes C, we can conclude that because our generators are in the vanishing ideal, that they cannot be computed in such classes C. So there's a variety of works where SV is the exclusive generator that's used, and in all such cases, our generators are not computable by the classes hit in those works. So in addition to computing a generating set, we also provide a membership test for the vanishing ideal. For the specific case of multilinear polynomials, it can be expressed in terms of partial derivatives and zero substitutions, and therefore has a somewhat combinatorial flavor to it. And that combinatorial flavor carries over to general polynomials, but it just gets a bit more technical. Implications of the membership test are, first of all, derivatives and zero substitutions are complete for reasoning with RFE and SV via this membership test. So if you can prove that RFE or SV works to derandomize PAT for some polynomial P, then you can prove it by taking some derivatives and zero substitutions of P. To demonstrate the utility of this kind of completeness of reasoning, we show an alternate proof for polynomial time black box derandomization of PIT for read-once formulas. This result was originally due to Minahan and Volkovich, and one step of their proof is a bit ad hoc, but we replaced that step by something with a much more explanatory power based on our membership test. In addition to reproving known results, we make some new progress on derandomization for read-once oblivious algebraic branching programs, ROABPS, which we'll define later. So that's my brief summary. Here's an outline for the rest of the talk. So first, I'm going to define SV and RFE, and then we'll talk about the equivalence of the two, and then we'll look at the generators for their vanishing ideal, and then we'll take a look at this membership test, and with both of those, we'll see some of their consequences. The Shpilka-Volkovich generator is defined in terms of some parameters. So for each variable xi, the generator requires selecting a distinct scalar from the ground field that we call an abscissa. The abscissa for xi is just denoted ai. From here, the generator SV1 can be defined as taking in as seed two variables y and z, and then substitutes for xi z times the ith Lagrange interpolating polynomial as a function of y. So what this does is if you plug in, say, ai for y, then xi gets z, and the remaining variables get 0. Okay, and that holds for all I. So you can view SV1 as interpolating every point with at most one non-zero coordinate, and it does so in a smooth way. for general positive integers L, SVL can be defined as the sum of L copies of SV1, each one getting a fresh seed. Properties are, as SV1 contains the points of Hamming weight at most 1, SVL contains points with Hamming weight at most L. And more generally, it has this property known as L-wise independence, and serves as a analog to that in the algebraic setting. The rational function evaluation generator is defined as follows. So it has parameters too, and just like SV, for every variable there is a distinct abscissa. It also has parameters k and l that give us bounds on the seed. And the generator for RFE KL takes as seed a univariate rational function, where the numerator has degree at most k, its parameter, and the denominator has degree at most l, the other parameter. The substitution performed by RFE is just that xi gets the evaluation of the seed f at the abscissa for xi. As an example, for k equals 1 and l equals 2, a typical seed would look like this. We have this univariate rational function in alpha, c1 alpha plus c0 over d2 alpha squared plus d1 alpha plus d0. And the substitution for this is xi gets the same expression, but with the abscissa for xi replacing alpha. And the key point to note is that this rational function f, the numerator degree is again bounded by k, which was 1, and then by the denominator degree was bounded by 2, which is l. And this notation RFE KL, we put k over l to represent the degree bound on the numerator over the denominator. So these generators, SV and RFE, are equivalent. I'll show that for the case of SV1, which is very strongly equivalent to RFE 01. So I'm going to start by writing down the substitution for SV1, just reproduced from the previous slide. And then the first step is we're going to just get rid of this denominator that's on the right, and we're going to just absorb that into the variable xi by rescaling it. So we get a new substitution that looks like this, where xi tilde is a rescaled version of xi. Then we're going to rewrite this as a product of two terms, where the first one does not depend on the index I, and the second one depends only on the index I and not on the other indices. And then we're going to reparametrize the seed, so this underbraced segment is going to get replaced by just a new variable z prime, and you can view this as just a change of variables. The resulting substitution for xi tilde is just z prime over y minus the abscissa for xi, which is really just the evaluation of a rational function at the abscissa for xi, where the rational function has degree 0 as a function of alpha in the numerator, and is degree 1 in the denominator. And if you think about it as z prime and y vary, you get every rational function with these degree bounds. The change of variables and the rescaling of the xi's, these are both invertible. So what we conclude is that plugging SV1 in for x for any polynomial p gives you 0 if and only if plugging RFE01 into these rescaled variables, xi tilde, gives you 0. So this is the sense in which these vanishing ideals are equal. SV1 and RFE01 have the same vanishing ideal up to this variable rescaling. And we just say that the generators are equivalent. So SV and RFE are equivalent more generally. So for the case of general L, SVL is, recall, is the same as the sum of L independent copies of SV. By the previous equivalence, SVL is equivalent to the sum of L independent copies of RFE01. And the latter, if you have a sum of L rational functions with degree 0 over degree 1, then by giving them a common denominator, you get a single rational function of degree L minus 1 over degree L. And you can reverse this process using partial fraction decomposition, and this establishes an equivalence between a sum of L independent copies of RFE01 and RFE L minus 1L, and therefore SVL is equivalent to RFE L minus 1L. For derandomization, again, this means is that for any class C, SVL derandomizes C, if and only if RFE L minus 1L works to derandomize C. You can consider RFE with more general parameters, k and l, and by just increasing k or l as appropriate, you can get to a set of parameters that's equivalent to SV by at most doubling the length of the seed that's necessary. And so for the purposes of polynomial time derandomization, RFE and SV are strongly equivalent. So next up, we're going to talk about generators for the vanishing ideal. I'll start by constructing them and then telling you how they generate. So let's fix a seed, g over h, for RFE KL. So the degree of g is the most k, the degree of h is the most l. And we're going to write down this expression that is linear in the coefficients of h and g and expresses the substitution as an equation. So making explicit the coefficients of g and h, we can collect this equation as I varies into a system. So the system looks like this. The point is that by looking at the system, we can see that if we plug in RFE KL and for the xi's, with respect to the seed g over h, then this matrix has a non-trivial linear dependence of its columns, namely given by the coefficients of h and g. So what this means is that if we look at any full-size square submatrix, its determinant is going to vanish when we plug in RFE KL for any seed. Meanwhile, the determinant that you get is, without the substitution, is non-zero. And so this polynomial, that's the determinant without the substitution, must be a non-zero polynomial in the vanishing ideal. So these polynomials are important. We'll give them the name elementary Vandermonde circulation. They're formed by selecting distinct rows from the system, or distinct variables, I1 through ik plus l plus 2, and you form this determinant out of it. So here's an example of EVCs 0, 1 with indices 1, 2, 3. It's this determinant right here. Expanded as some monomials, it looks like this. So we can see right away that this has degree 2. It's a multilinear polynomial. Each variable appears with degree at most 1. And every monomial that's consistent with that description in x1, x2, and x3 appears with a non-zero coefficient in this polynomial. So these properties hold in general. EVC is homogeneous to degree l plus 1, and it's multilinear. And every monomial that's consistent with that description and the relevant variables is present with a non-zero coefficient. So the EVCs do generate the vanishing ideal of RFE. This is a theorem. Sketch of the proof. We're going to first write down this ideal generated by the EVCs, and we're just going to compare it to the vanishing ideal. So because the EVCs belong to the vanishing ideal, the ideal they generate is a subset of the vanishing ideal, and so we just need to show the other inclusion. We do this by doing a multivariate polynomial division by the instances of EVC, applied to any polynomial in the vanishing ideal for RFE KL. And the result is a structured remainder term. And what we do is we show directly that RFE KL, when you plug it into any non-zero remainder with that structure, then the result is non-zero. Since plugging RFE KL into EVC gives you 0, this means that the only way that plugging RFE KL into a polynomial can have 0 result is if the remainder has 0 result, and that's only if the remainder itself is 0. So that means that any polynomial in the vanishing ideal, when we do this division, has to have a 0 remainder and therefore belong to the EVC ideal. Just a brief note on what this structure is. There's a set C of k plus 1 variables, and every monomial that's in the structured remainder uses only variables in C and at most L other variables. Okay, so that's the generating set. We can derive some consequences of this. So first of all, we can derive some basic properties of the vanishing ideal. First of all, the minimum degree of any non-zero polynomial is L plus 1. This is witnessed by EVC. The minimum sparsity is k plus L plus 2, choose k plus 1. This again is witnessed by EVC. And then among set multilinear polynomials, which are polynomials where you partition the variables into sets, and every monomial has to use exactly one variable from each part of the partition, we show that for every set multilinear polynomial of degree L plus 1, each of these can only be in the vanishing ideal if, moreover, each of these partitions has size at least k plus 2. So this is not witnessed by EVC, but it's witnessed by a related construction that I won't give here. We also conclude some lower bounds using prior derandomization results that use SV. So EVC belonging to the vanishing ideal cannot belong to any class that we know SV works to derandomize. Since EVC is really explicit, this is a nice lower bound. So that's our generating set. Next, I'm going to move on to tell you about the membership test. So let's fix P to be a multilinear polynomial. I'll just tell you the test for multilinear polynomials. The theorem states that P belongs to the vanishing ideal if and only if, so it's a precise characterization, both of two conditions hold. First is kind of a non-triviality condition. First, P can have no monomials that use very few variables, at most L, nor almost all the variables, in other words, all but K. So for polynomials that don't meet that restriction, the second condition kicks in, and it says that P belongs to the vanishing ideal only if, for every way of choosing K0 substitutions and L partial derivatives, such that they're all on different variables, the resulting polynomial, when you apply those operations to P, has to vanish when you substitute a RFE with a particular seed that depends on the sets K and L for your zero substitutions and partial derivatives. So the substitution looks like this. So something I'll point out is that in the special case where K and L are constant, so for example you're trying to do polynomial time, black box derandomization, the number of conditions to check here is only polynomials, comparably quite small. We conclude from this statement that zero substitutions and partial derivatives are complete for reasoning with reasoning about whether RFE or SV hits a given polynomial. In particular, we could suppose that we know that RFE-KL works for some multilinear polynomial P, and perhaps it's through some very difficult complex means. The membership test says that in fact there has to be a structured way of proving this, namely either P has a monomial with few variables in it, or a monomial with all but few variables, or there are K0 substitutions and L derivatives, so that when you apply those to P, the result is non-zero at this very specific point. So as an example, we reprove the result of Minahan and Volkovich that one copy of SV works to derandomize PIT for Reed-Wants formulas in a black box fashion. The critical step involves considering the sum of two variable disjoint polynomials, and whereas MV had a somewhat ad hoc argument, you can think about it in terms of the membership test, where each of those three bullets above constitutes an obstruction for P to belong to the vanishing ideal, and when you have a sum of two variable disjoint polynomials, any obstruction for either term in the sum is automatically inherited by the entire sum. Okay? And that explains why if SV hits P1 or P2, then it hits the sum. Okay, so that's Reed-Wants formulas. It's an old result. So next up, I'm going to talk about a newer result, which relates to Reed-Wants Oblivious algebraic branching programs. So briefly, they look like this, in the sense that they're a graph. Each of these edges should have a polynomial in it that's univariate in the variable that's written below. Think of each of these MIs as encoding what are think of it as a matrix of the polynomials on the edges between each layer. And then the polynomial computed by the ROABP is formed by taking the sum over all paths from the left to the right of the product of the polynomials along that path. So critically, every variable appears in exactly one layer, or between every pair of layers. And between every pair of layers, there is at most one variable that appears there. Every variable appears exactly once. So another way to define this is just that ROABPs are polynomials that are products of matrices, where each matrix, its entries are univariate polynomials in the same variable, and moreover, each variable appears in at most one matrix in the product. So an important parameter of ROABPs is their width. In terms of the graphical picture, it's the largest number of nodes in any of these gray boxes. In terms of the matrix representation, it's the largest dimension of a matrix in the product, row or column. Constant width ROABPs are at the frontier of research in PIT. A lot of people have tried, and we have a lot of special cases and some black box derandomization that comes very close, but they're still out of reach for us. And we won't resolve that today, but we make some progress towards it. Specifically, we give as a proof of concept of this overall approach we take through studying the vanishing ideal. What it can be, the result we have can be stated as a lower bound, where every ROABP that computes a non-zero polynomial in the vanishing ideal for SVL, if it moreover has degree L plus 1, then you get a lower bound on the width of that ROABP that grows with L. Okay. So this lemma, this lower bound applies to EVC, L minus 1L, and others, any degree L plus 1 polynomial in the vanishing ideal, and it extends to any polynomial with a non-zero degree L plus 1 homogeneous part as well. So in terms of derandomization, what this theorem looks like is that SVL works to derandomize PIT for ROABPs of width less than this bound that contain a monomial with the appropriate degree. So stated this way, I think one of the reviewers called this strange, which I don't necessarily disagree with, but if you view it in terms of the lower bound, it's kind of clearly handling a special case of proving lower bounds for the entire vanishing ideal, and it's a natural starting point, namely the least degree for which the vanishing ideal is non-trivial. So in particular, if you could generalize this lower bound to every degree, then you would have a full derandomization, full black box derandomization for constant width ROABPs. So that's our progress there. Along the way, we needed, most of our results rely on a particular technical lemma that we call the zoom lemma. I'll show it to you for multilinear polynomials. So the idea is that we need a technical lemma that lets us show when plugging RFEKL into P is non-zero. And the way this lemma works is you prove it by zooming in on a subset of the monomials in P. So for a multilinear polynomial, you select these, in general, you select these disjoint sets K and L. And then for multilinear polynomials, you look at taking derivatives with respect to the variables in L and zero substitutions with respect to the variables in K. So this has the effect of throwing out any monomial in P that either depends on a variable in K or does not depend on a variable in L. So it's got this combinatorial flavor of zooming in on a subset of the monomials. The lemma states that if this zoomed in polynomial does not vanish at a particular substitution that looks like a substitution of RFE with the same familiar seed of FKL that we saw at the membership test, then we can conclude that RFEKL, if you plug that into P, you get a non-zero result, where K is the number of zero substitutions and L is the number of derivatives. So as a brief sketch of the proof, the idea is that instead of parametrizing RFE by the coefficients of the numerator and denominator, we parametrize it in terms of the seed's roots and poles. And then we plug RFE into P, and then we do a Laurent series expansion near the roots and poles of the specific seed, FKL. And the point is that through some degree considerations and thinking in terms of the multiplicity of the roots and poles, and what this means in terms of the Laurent series, we can focus on a particular coefficient of the Laurent series, and it turns out that that coefficient is non-zero as long as this evaluation of p hat is non-zero. Coefficient is proportional to p hat's evaluation at this point. So that's more or less the proof. It gets a bit technical once you try to actually spell it out, but that's the high-level idea. So that's our zoom lemma. The last thing I want to tell you is something that doesn't formally appear in our results, but is still a conceptual perspective that was very helpful for us in developing these results initially. and it uses the language of alternating algebra. So I'm going to present it for you in the very special case of k equals 0 and l equals 1, and for degree 2 polynomials, in fact multilinear polynomials, because this lets me phrase everything in terms of network flow, and then alternating algebra is just the language that you need to generalize this to higher parameters. So EVC, recall EVC stands for the elementary Vandermonde circulation. So we'll see this connection with network flow is actually where the name comes from. So we're going to start by looking at EVC, 0, 1. And when you expand it out as monomials, it looks like this. The idea of the representation is that this is not very helpful as a way of looking at this polynomial. You want something that's more helpful. So we're going to take the step of representing it graphically. So we're going to make a graph where every variable gets a vertex, and between any pair of vertices, we're going to have an edge representing the monomial that's the product of those variables. And then for every coefficient of a monomial, we'll just put that on each edge, corresponding edge, as a weight. So that gives us this picture for EVC. And something that's worth pointing out is that any multilinear degree 2 polynomial can be represented in this way. So all we're doing is taking the coefficients and normalizing them. So the next step is we're going to try to eliminate some of the apparent complexity that's not necessary here. Namely, if you look at this weight on the edge between I1 and I2, it's this determinant, and this determinant actually doesn't depend on I3 in any way. Okay, so it's going to be the same weight for any instance of EVC as long as it uses I1 and I2. So the idea is just to normalize that out. And when you do, you get a picture that looks like this. So I've drawn arrows in here to represent that these edges become oriented, and this reflects the fact that the determinant has an orientation to it in the sense that the order of I1 and I2 affects the sign of the determinant, and reversing the order of I1 and I2 in the determinant causes a negative sign. So I'm capturing the order of I1 and I2 in the determinant by the direction of the edge in this visualization. I could just as easily make my rule go the other way, and what happens is the edges turn around, but also the coefficients pick up a negative sign. And the point is that even though these look like different ways of putting ink on a page, they represent the same underlying object, and this connection with network flow is realizing that the object they represent is this simple unit of flow around a 3 cycle. So I'm going to reproduce a few different ways of choosing these orientations, but all representing the same 3 cycle of flow. So 3 cycles of flow are interesting because you can't break them down into smaller units of flow, so we can call them elementary circulations. So EVC is a rule that says you give it 3 vertices, and it gives you this elementary circulation in this representation. Meanwhile, if you close the EVCs under linear combinations, then you get the degree 2 part of the vanishing ideal. This is because the EVCs generate the vanishing ideal. Meanwhile, elementary circulations generate all circulations under linear combinations. So what this means is that the degree 2 part of the vanishing ideal is, in this representation, the same thing as the polynomials that can be represented as circulations. So I find this conceptually appealing, so hopefully you do too. There's also this equivalent, or this understanding of circulations as these kind of flow-like objects that satisfy conservation. So at every vertex, the flow in equals the flow out. And you can apply this characterization to this understanding of EVC and the vanishing ideal, and it turns out that our membership test is just a way of restating conservation of flow in this representation. So as I said before, this is the specific case of k equals 0, l equals 1, and degree 2. In order to generalize it to higher k, l, and degree, you want a higher dimensional version of network flow and a language for that, and that's what alternating algebra more or less provides. Okay, So that's all I have to say about that, except I'm going to give you an example. So let's consider this polynomial. If you look at it, it's not clear whether or not it belongs to the vanishing ideal. But if we convert it into this representation, you'll see that it forms a simple 5-cycle, and therefore should belong to the vanishing ideal. And indeed, if we take this 5-cycle and break it up as a sum of 3 cycles, you note the cancellation on these edges that are common to the 2 3 cycles, or common to 2 3 cycles, then that tells us how to write P as a sum of EVCs. In particular, we have this 3-cycle 1 2 3, another one 1 3 4, and another one 1 4 5, and that gives us tells us what EVCs to create, and then adding them up, it gives us P. So that's this understanding of the vanishing ideal that we found very helpful, and hope you do too. So in summary, we took a look at a particular generator, the rational function evaluation generator, and through studying it, kind of demonstrated the utility of rational function substitutions as generators instead of just polynomial substitutions. We also demonstrated the systematic approach toward de-randomization by looking at the vanishing ideal, and in particular proved some results for ROABPs. On the technical front, we proved that RFE is equivalent in a very strong sense to SV, and we provided a generating set for the vanishing ideal of RFE and SV, in particular also a Grubner basis. We also provided a membership test for the vanishing ideal, and both of these last two we saw applications to de-randomization and lower bounds. But with that, that's everything I have, so thank you so much for watching.